Okay, welcome to the first IB, HL and SL. I guess it's kind of, right now we're just doing Unit 5, so this is stuff for both HL and SL students. So today we're just going to be covering Unit 5. I don't know why that went white, but that's 5. Fine, Unit 5. And Unit 5, just like you see in your textbook, is called energetics. Energetics and thermochemistry. So you should see from this thermo has chemistry to do with either the absorption or the release of heat, whether the reaction is exothermic or endothermic. So thermochemistry. Okay, so energetics and thermochemistry. Right now we're just going to cover this in a lot of different sections so that the videos can stay to 10 minutes or basically less each, or 15 minutes or less each, and then basically eventually I'm just going to release some question solving videos, how to work through the problems, how to think about them and how to approach the problems. So we're going to start off just with thermodynamics. What is thermodynamics? So that we know why we're studying this unit. Thermodynamics. So what is thermodynamics? Thermodynamics is basically just the study of energy. It's the study of energy. And basically, with the study of energy, it talks about how is interconverted, the study of energy, and how we can convert it, right, to useful energy. It's always a waste, making useless energy. There's no point in just, starting a fire and then walking away and not enjoying something about it, right? So we want to do a study of energy and how it's interconverted into something useful. So study of energy and how it is converted. Basically, we like to convert energy. We convert chemical energy into mechanical energy in our cars. So we need to do the conversion of energy. We need to convert, hydroelectricity into electricity. How do we do that? So all of that can have to do with thermodynamics. So it has to do with studying, the heat of the system. What does the heat cause? What does an increase in pressure, an increase in volume cause? So that's all stuff. So this first lesson is just going to be the very basics of it. The study of how it is converted, how it is interconverted. So the first law of thermodynamics that we should know, the first law is that energy can be converted. So energy can be converted. And this is basically yeah, so energy can be converted from one form to another. So we can convert chemical energy to physical energy, mechanical energy. We can convert, electrical energy to mechanical or chemical energy and electrolysis, per se. So energy can be converted from one form to another. So energy can be converted from one form to another, but this is the important part. But, and this is in a closed system, the total energy of the system, but the total energy of the system remains constant. So what this means, though, it depends on what we define as the system, right? We can always say, if we can define, we can look at the Earth as a system, right? So any chemical reaction that occurs on Earth, if we're converting, if we're burning methane, if we're burning it to form CO2 and H2O, the thing is that, so let me just finish this, plus O2. O2 plus CH4 releases CO2 and H2O. So basically, the extra stability gained by the CO2 bonds and the H2O bonds it makes the system more stable and therefore releases heat energy, right? If we've got less stable atoms reacting to form something more stable, the energy between the instability and the stability gets released as heat energy. And this heat energy is going to go into basically into the air, into the atmosphere, depending on what we're using it for, right? If we're using it for cooking, right, we use methane in order to form the blue flame, and then we put that blue flame directly onto the bottom of our frying pan, and the heat is converted. The heat is converted from chemical energy of burning CH4 from CH4 and O2 into heat energy, and we use this heat energy to cause a chemical change in our food. Chemical change to cause the chemical change. So you can just see it is a conversion, right? We're converting. Of course, there's loss, right? We're going to lose that heat to the air. We're going to like basically the surroundings. So we're going to lose the heat to anything in the surroundings, right? You've got on top of your stove, you've got your flame coming out, but you even got that metal rack on top of it where you put your pots and pans. That metal rack heats up. So that is wasted energy, right? We've heated up a piece of metal that we don't care about heating up. We're not doing anything on that except we're just resting a stand on top of it. So basically we're just studying, in this unit, we're just going to be studying like what is a useful energy conversion, what in that case is a useless, right? You heat the air around you, it's a warm day, especially here in Mexico, it's 30 degrees outside. You don't really need to heat your house by burning the methane, but when you burn it, just as a byproduct, you're heating, you've got that flame, but the oxygen in the air is coming into the flame, the nitrogen, the argon, everything is going through that, and they're taking that heat energy and they're converting it into kinetic energy. So you can see, like, anytime, even when we light just a simple flame, we have a lot of energy conversions undergoing, or we're undergoing many, many basically energy conversions. So, as I said, this is just basically an introduction to this section. So we need to look at the introduction to the units that we're going to be using in this the units that we're going to be using in this unit. Yeah, that sounds a bit weird, but in this unit, we need to know that we're using the Kelvin scale rather than the degree Celsius scale, right? The degree Celsius scale was basically formed just to say water freezes at 0 degrees Celsius in standard conditions at regular pressure, 1 atmosphere pressure, and it boils at 100 degrees Celsius. So that's why the Kelvin scale, and then they took whatever this temperature was, they divided it by 100, and they said, okay, each one of these is 1 degree Celsius. Because, right, the temperature scale, it's just something that's made up. It's something that we use in order to measure the kinetic energy of the gas particles that surround us, the kinetic energy of the air, right? So basically, all of these scales are just man-made scales. It's somebody just took a value and said, okay, this value is very important. Everybody has access to some water. This value is important. Everybody has access. You can create this scale yourself. Kelvin scale works a little bit different. So it starts from zero, and it's a capital K for Kelvin. So just like degree Celsius is a capital C, not a degree and a small c, right? That's not how you write degree Celsius. So it's Kelvin is 0, and 0 is absolute 0. And we're going to go over the implication of what is absolute 0. And then aside from that, it's broken every degree Kelvin down into the same increment that degree Celsius are measured in. So 1 Kelvin, 2 Kelvin. We'll see the conversion factor right now. So the Kelvin scale, what it is it's degree Celsius plus 273.5 Kelvin. So plus 273.5, and their units are Kelvin. So basically, at 25 degrees Celsius, if we were to convert that to Kelvin, you do Kelvin equals 25 plus 273.15, or 0.15, sorry, 273.15, and then you come out with your Kelvin is equal to 298.15 Kelvin. So that's the temperature in Kelvin. So we can easily interconvert from degrees Celsius to Kelvin and from Kelvin to degrees Celsius. So watch out for this part, because right, it's an easy question they can ask. They can have something like, ensure your results are presented in Kelvin, or present your final results in degrees Celsius, and you must know how to do the conversion. You take Kelvin minus 273.15 and you get the degrees Celsius. Okay, so basically we're going to talk about, really quickly, we're just going to talk about the potential chemical energy. Potential energy. So right, there's energy contained within every single molecule. But the thing is that the way that we rate this is that the stronger the bonds, is more stable, is a more stable compound. And weaker bonds is less stable. So what we do when we do a chemical reaction, right? It's every chemical has potential energy. But what we need to look at, the potential energy difference, the difference in potential energy. So basically with this will relate back to what you guys did last year in IGCSE, is your delta H value, right? Your delta H is you want to find the delta H of your reactants, and then minus off the delta H of your products. So what that means, right, the delta H was we were calculating the bond energy. So we calculate, you've got CH4, so you take C is bonded to H, 4 H's. So C is bonded to 4 H's. So you do 4 times the energy of a typical CH single bond. So what you can see is, remember when we said delta H, if delta H is negative, the reaction is exothermic. And we're going to cover this more in the next video, don't worry if you haven't done IGCSE. And delta H positive means that it requires energy, it's endothermic. So we're going to relate this over here. Let me just change the color a little bit. Weaker bonds means less stable, and stronger bonds means more stable. So that's the thing, is that if your reactants are more unstable or less stable than your products, all the extra energy gets converted is exothermic, gets converted into heat energy. Whereas if we have very, very strong bonds, right, and we minus off our products, we're going to have a positive value. And that means if we want to make something go from somebody, so heat, so I'll just say this is absorbed. So basically, if we want to go from a very stable system, right, if we want to go from something stable, right, we all know CO2 is very stable, and that's why, it's a difficult greenhouse gas to get rid of, but CO2 is really stable. If we want to convert it back into carbon and oxygen, we need to apply energy to that system. We need to add in a lot of energy in order to decompose carbon dioxide back into carbon and oxygen. Whereas we know is the reverse reaction, right? We burn coal and we produce heat. So we know the reverse reaction produces heat. So the forward reaction must absorb heat. We have to put that same amount, whatever heat we lost from the system, we need to put that same amount of heat back in. And usually that heat we need to create somehow. So we either need to create through coal power plants. So again, we're just burning something in order to reduce carbon dioxide. So you're going to get nothing from that. Or we can use renewable energy. We can use solar energy. We can use hydroelectric energy. So using renewable energies, we can force this reaction to happen. We can use electrolysis to start breaking down products. But typically, this reaction wants to occur. The reverse reaction wants to occur. Carbon wants to react with oxygen because these bonds are weaker. The bond holding oxygen together, the O double bond, is weaker than the carbon oxygen double bond because they're both electronegative, so they can't pull those electrons like they want. And here they can both pull the electrons. They can pull the electrons off of the carbon. So okay, I'm going to move up to the top here, I guess. We'll just erase this part off. So okay, this might just take a second to erase it all off. There we go. Yeah, it looks good. It's good enough. Okay. So basically, yeah, that's all we're going to be building on is through thermodynamics and through thermochemistry, we're just going to be talking about the stability of the bonds, whether the reaction is going to proceed, whether the reaction is not going to proceed, whether it's endothermic or exothermic, whether it's spontaneous or non-spontaneous. So we're going to be seeing a lot of different things in this unit. So right now, just to finish up, all we're going to cover up is we're going to cover heat. So what is heat? Heat in IB has the unit of Q, is considered, the symbol for heat is Q. And what it is basically heat is a measure, it's a type of temperature. That's the heat of the system, the temperature of the system. And heat always moves from hot to cold. So something warm always gets cold, and something cold, takes the thermal energy from something hot. Something hot doesn't take the energy from something that's cold. It's slowed down by something that is cold. And there's three ways of transferring heat, and what these are is it's conduction, which we'll go over in a second. There's convection, and finally there's radiation. So conduction, that's basically right. Let's just you take a metal stick, you put it into a fire, and eventually that metal stick heats up here. This guy starts to vibrate a lot, and his electrons are going around bouncing into everything because it's got that delocalized electrons in metals. So he vibrates his neighbor, vibrates his neighbor, vibrates the neighbor, vibrates the neighbor, and eventually that heat gets transferred through the solid to the end of the stick, where hopefully your hand isn't there to grab and go, ah, no, that hurts. For convection, this is a little bit different. So what convection is kind of like, if you guys ever realized in a chemistry lab, when you're heating up a solution, you can actually see, if you look at it, and I recommend you guys do this when we get back to school, you look at, and you can actually see things moving. You can actually see the solution moving. And what that is, that's convection currents, basically. The bottom of the container, right? You've got the Bunsen burner. I'm just going to draw up with heat. The Bunsen burner is heating up this container. So when you heat up a liquid, what's going to happen is that the density of the liquid at the bottom is going to lower in density. It's hotter now, so the molecules can spread apart more and more and more, and the density decreases. So when the density decreases, what it does is that the high density colder liquid at the top moves down to the bottom, and the low density hot liquid at the bottom moves to the top. So it's like an auto stirring mechanism. It's all the hot molecules go to the top of the container, and all the cold molecules go to the bottom. Then they absorb heat, they heat up, and they basically stir themselves around inside the solution. So I highly recommend you looking at it. And the last one is radiation energy. So that's heat energy is in the IR wavelength energy. So infrared radiation. If any of you have ever been in an infrared sauna, It's the exact same thing. You don't actually see the light. There's just incident IR light on your skin, and all of a sudden you start sweating in no time. So radiation energy, basically this is energy that causes atoms to vibrate over a longer distance. So this is, it causes the bonds, you know, so if we had like uh, water, so it can absorb IR radiation. So what happens is that these bonds start to vibrate more, and when they vibrate more, right, they create friction with other water molecules in solution. So they create friction. By creating friction, you can increase the temperature. You know, you increase friction, you increase the temperature. So IR radiation, the best example would just be something like, you know, a glowing red hot piece of metal. It's emitting its heat as light, and you know, when you get close to that piece of heat, it's gonna feel hot, and you could block out IR radiation, right? It's if you've ever done it before, basically, you can just stand in front of a fireplace and hold something in front of yourself. Maybe you've been there in the summer, and you're having a big fire, and you sit there, and your face is getting hot. You know, I'm gonna draw a little like he's got some spiked hair. Your face is getting hot. The fire's right here. Your face is getting hot, so you put your hand in between you and the fire. So basically, right, convection is working up and down. There's no conduction because the conduction would only occur if you were holding something into the fire. But what's happening is that basically all these IR waves coming out from the fire, when they hit your skin, they're very, very hot. When you block it with your hand, all of a sudden your skin starts to cool down and your hand starts to get hot instead. So that's IR radiation of a fire. So okay, that's all, pretty much all we have to do in this video, and we'll continue on later.